Good systems don't avoid failure, they decide where it happens. We often say we designed for failure, so we add retries, timeouts, queues. We try to make the system resilient, but what we're actually doing is allowing failure to move through the system without ever deciding where it should stop. Because failure doesn't stay where it starts, it propagates. A slow dependency becomes a timeout becomes a retry becomes additional load, and that load doesn't disappear. It shifts into another service, another queue, another layer of the system. This leads to a very specific kind of behavior. The system doesn't fail, it degrades. Slowly, inconsistently, and often without a clear signal of where the problem actually is. Most resilience patterns don't prevent this, they contribute to it. Retries multiply demand, queues accumulate pressure, timeouts push work downstream. Each of these patterns is useful, but only if you control where their effects end. And this is where the real decision sits. Not in how you handle failure, but in where you allow it to exist. Because in practice, you are choosing between two outcomes. You can reject requests early, or you can accept them and let the system attempt to process them under stress. The second option feels safer. It avoids immediate failure, but it introduces something far more difficult to control: distributed degradation. Let's make this concrete. You have a system. A user request enters through an API. It triggers compute, which depends on a downstream service. Under normal conditions, latency is low, but under load, the downstream service slows from tens of milliseconds to seconds. At that point, nothing has failed yet, so the system continues. Requests are accepted, execution time increases, timeouts begin to trigger. Retries are introduced. Now each request results in multiple attempts. Concurrency increases, queues begin to form. Execution environments are saturated. At this stage, the system is no longer processing user requests efficiently. It is processing its own recovery mechanisms. And the user experience reflects that. Requests take seconds. Sometimes they succeed. Sometimes they fail. From the outside, the system appears unstable. Now consider a different decision. You introduce a boundary at the edge. At the API layer, you enforce rate limits. You define a maximum acceptable latency budget. You monitor downstream health. And when those limits are exceeded, you reject the request immediately. No compute is triggered. No retries are initiated inside the system. No additional load is introduced. Failure happens at the boundary before the system absorbs it. This changes the behavior of the system entirely. Internally, services remain stable. Queues do not grow uncontrollably. Retries do not amplify load. The system continues operating within its capacity. The user experience also changes. Instead of waiting, the user receives an immediate response, a clear signal. The system is currently unable to process the request. This may appear more aggressive because failure is now visible, but it is also predictable. And importantly, it does not degrade the entire system. So the trade-off is not between success and failure. It is between visible, controlled failure at the edge and distributed, uncontrolled failure inside the system. As architects, this is the decision we are making, whether we state it explicitly or not. From an implementation perspective, this becomes concrete. You enforce limits at ingress. You constrain concurrency and compute. You use queues as boundaries, not as infinite buffers. And when work cannot be completed, you allow it to fail, without reintroducing it indefinitely. None of these mechanisms remove failure. They define where it stops. And that is the role of architecture here. Not to eliminate failure, but to decide where it is allowed to exist. Because if that decision is not made explicitly, it will still be made by the system, under load, and usually in the least controllable place.